Hey everybody, Dr. A here, and in this video we're going to be exploring another example of average normal stress. So let's go ahead and get started. In the given information, we're being told to show that the average normal stress value when analyzing a left free body diagram, which I'm calling sigma L, is equal to the average normal stress value when analyzing a right free body diagram, which I'm calling sigma R. And then I'm asking you to compute the stress in megapascals. So we gotta practice some unit conversions here. All right. So let's go ahead and get started. Now, as we have said before in another video, method of sections is a statics process. It's really not new in mechanics of materials, but we use it a lot in mech of materials. And so by method of sections, what we do is we pass a cut section through a member, and then we analyze either one side of the member or the other. Now, as we've said before, and as you learned in statics, it doesn't matter which side of the cut section you analyze. You can analyze the left or the right, or if you have something oriented vertically, you can analyze what's going on above the cut section or below the cut section. But you just have to be careful. You have to be mindful of what's there, okay? And that's what this example is meant to exercise for us, okay? So I'm going to say we're going to use MOS, and we're going to say to cut a section through the member, okay? And so if I take this member and I look at an overall free body diagram of this member, okay? So I'm not actually cutting it yet. Here's 3 kilonewtons. And then at this fixed end at B, what do I have here? Well, technically I have a normal force NB. I'm going to have a shear force VB, and I'm going to have a bending moment MB. Okay. Now, by looking at this, hopefully we can tell that VB is 0 and MB is also 0. Why? Well, it's because the system is an axially loaded system, right? So the only applied force is lying along the longitudinal axis of the member. So it's axially loaded, which means that you have nothing generating a bending moment, and there is no applied force with a vertical component that is going to generate a shear force. So it's all in tension or compression. All right. So if we look at this overall free body diagram, the only unknown reaction we really need to solve for is NB. So I'm going to say sum of the forces in the x direction equals 0. And I'm going to say 3 kilonewtons plus NB equals 0. Why am I making them both positive? Well, in my equilibrium equation, I said vector forces pointing to the right are positive. 3 kilonewtons is pointing to the right, and I assumed NB was pointing to the right. Okay, remember this direction right here is an assumption. All right, I apply my equilibrium equation, I do the calculations, I get NB is negative 3 kilonewtons. What does that negative mean? It means that NB is actually 3 kilonewtons pointed in the opposite direction of what I assumed. So that means that NB is, in reality, it's pointing to the left, okay, because it came out negative here. Now, whenever you have NB pointing towards the system, all right, you can write that also as 3 kilonewtons in compression, all right, at the reaction point. So all of this is statics right now, nothing new, all right? Now, what about this method of sections? I said use method of sections to create a cut section through the member. So I'm going to make a cut section through here, and I'm going to look at either one side or the other. So let's start with a left free body diagram, left FBD, all right? So here's my member, and there's that cut. And what's going to show up on the left side? Well, that 3 kilonewton shows up, of course. And what's going to show up at the cut? Well, at the cut, of course, I have a V left, I have an M left, and I have an N left, okay? And so, like we've talked about a few times now, the moment is 0, the shear is 0, and here in this left free body diagram, I can apply my equilibrium equation. Sum of the forces in the x direction equals 0, and of course I have 3 kilonewtons plus N left equals 0, so N left is negative 3 kilonewtons, which indicates we've got 3 kilonewtons in compression, okay? So there we go. That's looking at a left free body diagram. Now, what if I wanted to look at a right free body diagram? Okay, so what does that mean? That means I'm going to pass a cut through here. I'm going to look at everything on the right side of the cut. All right, so when I do that, I'm going to say right free body diagram. All right, here's that cut, and I'm looking at everything on the right side of the cut. So what is showing up on the right side of the cut? Well, that reaction that I calculated a few minutes ago is showing up, right? The reactions are on the right side, all right? So what am I gonna draw here? Well, I'm gonna draw NB, and what was NB? It was 3 kilonewtons, okay? How do I know that? Well, that NB being 3 kilonewtons, that was this work we did earlier. Notice we did this work here earlier before we ever used method of sections. We just looked at a free body diagram of the whole system, all right? And we got that axial or normal force reaction was 3 kilonewtons pointed to the left, which means it's in compression. So that's what this means right here, okay? This 3 kilonewtons is this NB, which is this reaction right here, okay? That's what that means. So now I've made this cut. I'm looking at a right free body diagram. And so what is going to show up at the cut? Well, I'm going to have a shear force. I'm going to call that VR. I'm going to have a bending moment. I'm going to call that MR. And I'm going to have a normal force that shows up here. I'm going to call that NR, okay? And I'm going to say sum of the forces in the x direction equals 0. And just looking at the x direction, I have negative NR minus 3 kilonewtons equals 0. In this drawing, they're both pointing to the left, okay? I do some rearranging. I get NR equals negative 3 kilonewtons, which means NR is 3 kilonewtons in compression. Now look at that. Look at that. What I've shown here is that the normal force in this segment, whether I look at a left free body diagram or a right free body diagram, I get 3 kilonewtons in compression. Now, if you want to draw a little sketch and kind of show them side by side, here's what you can do just to help yourself visualize it better. You can draw that left segment, and here's that cut. And then I'm going to draw the right segment, and here's that cut, okay? And, you know, there's that fixed connection there, all right? And so here was that applied force, 3 kilonewtons. And then at this reaction over here, we had 3 kilonewtons, right? 3 kilonewtons. And so what became visible here? Well, you had 3 kilonewtons in compression at this cut, and 3 kilonewtons in compression in the right cut. So if you look at any part of this system, if we look at a left free body diagram, it's in equilibrium, okay? Or if we look at a right free body diagram, it's in equilibrium, all right? So let's make a note here, okay? Both free body diagrams are in equilibrium. Another thing you want to note here, put another star here. If analyzing a free body diagram with support reactions, we must solve for support reactions before using method of sections. Okay, so if you say, hey, I want to look at a free body diagram on one side of a cut that includes support reactions, that means that you have to calculate those support reactions first before you do method of sections. So did we do that here? Yeah, we sure did. Going back here, we solved for those support reactions of that fixed connection before we ever made any cuts. That's what we did here in this dash box that I just circled, okay? Now, finally, we need the stress, okay? We got the forces are the same, right? So the cross-section area is also constant, right? So we're going to say sigma left is the left normal force over the area, all right? And that was 3 kilonewtons in compression. And what was that area? Well, it was a rectangle, right? So what I'm going to do is I'm going to convert that to units of meters. So that's going to be 0.05 meters by 0.025 meters. Okay, so that was the cross-section area. And I'm going to say, 3 kilonewtons divided by 0.05 times 0.025. And what I get is 2,400 kilonewtons per meter squared. So again, what I did was I converted the 50 millimeters and the 25 millimeters to meters. I just divided by 1,000, right? That's how I got them in meters. And I got a stress as 2,400 kilonewtons per meter squared. Now, what is a kilonewton per meter squared? That is what we call 2,400 kilopascals. Now, what I really wanted was megapascals. So I'm going to say sigma left is 2,400 kilonewtons per meter squared times what? 1 meganewton over 1,000 kilonewtons. And so what you end up with is 2.4 meganewtons per meter squared, which is 2.4 megapascals. So the reason I did that again was the directions said, if we scroll back up, the directions said compute the stress in megapascals. All right, so I'm just following the directions here. So what about the right side? I'm going to say sigma R is the normal force in the right free body diagram divided by the cross-section area. And sure enough, that was also 3 kilonewtons divided by 0.05 meters times 0.025 meters. And surprise, surprise, you get the same final conclusion, 2,400 kilopascals, which is 2.4 megapascals. And both of these were in compression. So I'm going to go ahead and put a little C there for compression. Okay. 2.4 megapascals in compression, whether we look at a left or a right side free body diagram. Okay, so hopefully you found this video helpful. If you did, please hit like and subscribe, and thanks for watching.